Okay, so the second thing that we looked at today, standard F3 says that we need to be able to tell if a function is linear or not. And we've already been working with linear relationships earlier this year. So we're taking a lot of that reasoning that we already have and using it again, okay? So if I give you an equation, you should be able to tell me if it's linear or not. If I give you a graph, you should be able to tell me if it's linear or not. And same thing with the table. Well, that table will be very similar to one of our last problems from the beginning of the day, right? So if we're thinking about if something is linear, it's linear if there is a constant rate of change, okay? If we're looking on a graph, remember linear, the first four letters are a line. So if we were looking on a graph, we would expect to see a straight line, okay? So if we're thinking about when it's linear and when it's not, again, constant rate of change, we've said that. The graph is a straight line, we've said that. Oftentimes, most of this year, we've looked at y equals mx plus b. That is slope-intercept form, and also standard form that would look like that, ax plus by equals c. If it's written in those forms, or it could be, then it's going to be linear. But what's important, it says here that the variable doesn't have an exponent, and it says x, but actually x can't have an exponent, y can't have an exponent. So no variables have exponents. That's one thing that you'd be looking for. No square roots of variables. Okay, no variables in the denominator. Actually, let me write that on the next one. Sorry, guys. So, no variables in the denominator. That would be another thing that we'd be looking for. If there's a variable in the denominator that can't be like simplified and gone, then it's nonlinear. If there is a variable underneath a square root symbol, underneath the radical, then it's not going to be linear, right? If there are any variables that have exponents, it's not going to be linear. So no, this is not a mathematical term, but no funny business, right? We just want a plain x and a plain y. Okay, so that's what we're looking for. So if those things aren't the case, then it would be nonlinear. So then if we're looking at a graph, again, we would see a straight line. And it would have to be continuously straight, right? If you were to put your pencil down, your pencil would follow that line the whole time. Now, from a table, we want to look at if it is linear, there's a constant rate of change, which means that we need to look and see. So we're looking at finding the slope. So again, we need delta y over delta x. So if we go through and find our changes from -7 to -3, that is a +4. From -3 to 3, that is +6. From 3 to -3 is -6. And from -3 to -12, that is -9. And so when you do this, one super important thing, you have to look at every possible delta y over delta x. So you've got to make sure here there's two possibilities. I need to look at both of them. So I've got to write both of my fractions. So my first fraction for delta y over delta x is -6 over 4, right, coming from here. My second fraction then, my delta y, remember, goes on top, so that would be -9 over 6. And if we simplify, right, -6 fourths reduces to -3 halves, because we can divide both of them by the common factor of 2. -9 sixths, there is a common factor of 3. We could divide it. We also get -3 halves. And so because both of those are the same, there is a constant rate of change, so it is linear. And not only is it linear, but we know that the slope is -3 halves, okay? Some of you guys may have divided right here, and maybe you got -1.5 and -1.5. That would also tell you that it's linear, okay? So if we look at B, B has more points, so that means that we should have more fractions, okay? So same thing, we need delta y over delta x. So if we go through and find all of those changes, here the change in x is -9. Here the change in x is +3. Here the change in x is +12. Change in y, this is -12. Change in y is +4. Change in y, that went down 16. So now we're ready to make our fractions. This time we have to make 3 because there were more ordered pairs in the table. So delta y over delta x, my first fraction is -12 over -9. My second fraction is a +4 over 3, right? Here's my first fraction. There's my second fraction. My third fraction then is -16 over 12. And then we need to simplify or divide to find out, are these all equal? Is there a constant rate of change? So if I simplify -12 over -9, a negative divided by a negative is a positive. So I would get +4/3. Maybe you divided that and you got 1.3, right? The second one is already for a third, so it's looking pretty good. But if we look at the last one, that would simplify to be -4/3. So then the question is there a constant rate of change? And the answer to that is no, because this value is different than the others. So this example is non-linear. Okay, so we've talked about graphs, we've talked about tables. Let's talk about equations for just a minute. Right? There are 3 kinds of equations or 3 forms for linear equations. The first one we worked with a lot, slope-intercept form, y equals mx plus b. So for example, y equals 2x minus 3. What we need to know is that it might not look exactly like that, right? I could have y minus 3 equals 2x. But the important part is I could take this equation and I could write it in slope-intercept form. I could add 3 to both sides. And so I would get y equals 2x plus 3. Well, that is slope-intercept form. So even if it's not perfectly in these forms, if we can write it that way, it is linear, right? Standard form, something that looks like this, is also a linear relationship. This is called point-slope form. We're gonna work with that a little bit more as the semester progresses. That's something that you're gonna use a lot in high school. But that is also linear. So if we notice, all of the x's and y's in all 3 of these are just plain x's and y's, right? None of that funny business we talked about. There are no exponents. There are no square roots. None of the variables are in the denominators. Those are some of the examples that we would look at, okay? So take a few minutes and try these problems on your own, and then you can check your answers. Thanks, guys.